Thank you. Well, this is a school, and here's our teacher. So today I'm going to talk sort of two things. We're going to talk a little bit about information theory in general, or sort of information theory in the large sense. And then I'm going to talk some technical things, but only at a fairly low level. So I couldn't resist putting in at least a few technical things in my talk, but this talk is largely non-technical. So there are basically two parts to this talk. You notice the title here is Information Theory, Past and Present. And the past part is going to be what I'm calling a midpoint perspective. And since this is a school, I figured I better put some lessons in there. So there's 3 lessons learned. And what I mean by midpoint perspective is if you go, this is 2008, and so Shannon wrote his first famous paper in 1948, so 60 years ago this year. In fact, July, so 60 years ago next month, actually. It was published in Bell System Technical Journal. And I got my PhD in almost exactly the middle of then and now, so 1977. So my perspective is, if you think about when I was a graduate student, Shannon was as far back to me as my graduate days were to you. Okay? So that's what I mean by a midpoint perspective. And then I'm going to talk more particularly about wireless networks. And I'll try to tie these together a little bit, but wireless networks is where I mainly do my work, so I thought I would spend a bit of time talking about the future of wireless networks. I don't really have much to say about the future of other things, so that's where the future comes in. So let me just start out then by saying a few things about the past. By the way, can everybody hear me in the back? Can you hear me okay? Okay, thank you. So let me start out with this list of technology. So we're information theorists. We're sort of the theorists behind information technology. And these are, I try to make a list of information technologies that we all use every day and that we probably feel like our work somehow impacts. And I ask this question, what do they all have in common? Well, there's more than one thing they have in common, but I have one particular thing in mind. But let's just look at the list here. The internet, the web, cellular communications, the PC. These are all big, big things, right? Big, big information technologies. And then a lot of sort of lesser but equally interesting technologies, Bluetooth, sort of digital media, digital broadcast and so forth, JPEG, MPEG, MP3, GPS, DSP chips, flash memory, and then sort of more sort of researchy kind of things, MIMO, multi-user detection, all kinds of fun codes and things. So these are all I think these are sort of a list of things that we sort of hold near and dear and feel like we're contributing to and we're working on. So what do they all have in common? Well, one thing they have in common is that none of them existed when I entered graduate school. Okay? So these technologies have all been developed since I got my PhD. Most of them in the 80s and 90s. The internet, sort of the 80s and 80s, the web in the 90s, cellular in it's a continuing development, but started in the 80s. The PC in the early 80s, late 70s, and so forth. All this stuff came about after I graduated from graduate school. So what were we doing in graduate school 30 years ago when we didn't have anything to work on? So in other words, what did exist back in those dark ages? Well, what did exist was the intellectual basis for all these technologies. That is, all the stuff that hopefully you have studied in graduate school, coding theory, detection estimation, digital comm, DSP, information theory, probability and random processes. I took all these courses. This is what the courses I took when I was a graduate student, even though we didn't have the internet, the web, cell phones and all that stuff. I hope you took these courses too. So the important thing here is that this is really what I learned in school that was important. Any technologies that happened to exist at the time, they weren't very important actually, because all the good stuff we have now came after. So this is lesson number 1. Be sure you understand the fundamentals. okay, because that's really 30 years. You're going to have a career of 30, 40, maybe 50 years after you graduate from graduate school, and we have no way of predicting what's going to be happening technologically. No one would have predicted all that, any of that stuff that I put up there. It was all sort of not even in the consciousness at that time. So not only should you be sure you understand the fundamentals, but many of you are going to become college professors, and you should be sure that your students understand the fundamentals too. That is, don't let them overlook what's really important. So that's lesson number one. So let's look back 60 years at the past and take a sampling of things that were happening at that time. These are three major developments from 60 years ago today. In fact, they're almost completely contemporary with one another. One is the exposition of the cellular concept. That is, the idea that you could reuse spectrum by having small cells in a radio network. This was never published. It was an internal Bell Labs memo written in December of 1947. The guy who wrote it was a guy named D.H. Ring, which is a great name for somebody in the telephone industry. Then, also in December 1947, the transistor was demonstrated also at Bell Labs by Bardeen and Brattain. And this is the paper that describes that. It was published, of course, a little bit later. And then finally, of course, for us, the most famous thing that happened in that time period is the publication of a mathematical theory of communications, also, by the way, at Bell Labs. So think about what was happening. So if this happened in December 47, these experiments were done in December 47, and this was published in July 48, Shannon must have been writing this stuff up in December 47. You know, the review times were a lot shorter back in those days. So December 47, in the same place, all these great things were happening. And this is really the basis for all that stuff on the previous slide. The transistor, the cellular concept, and the information theory. So that's a long time ago, 60 years. Even I wasn't born then. What about 30 years ago? I just picked a sampling. This is what was happening when I was a graduate student at Princeton. By the way, because I'm the dean, it's obligatory that I use orange and black on all my slides, so you're going to get that imprinted in your retinas, and I apologize, but it's in my contract. So here are some things that were published. Now, these are all published in the Transactions on Information Theory. The Transactions on Information Theory, by the way, did not exist back in those days because information theory didn't exist until then. It was first published in the early 50s. By this time, it was fairly well established. But here's some things. I just picked a few out there. I could have picked a lot of things out. This one, this is Diffie-Hellman. This is sort of what makes public key cryptography work. This is Lepel-Ziv. This is what makes, you know, zip work on your computer. These are very, very important developments in information technology. This is Cover-El-Gamal. This has not been as influential in terms of the technology yet, but I put it here because it's been extremely influential in very recent times in research, right? I mean, the relay channel has taken on a very important role in our research work and also in technology as some of the new standards start incorporating relays in them. So these two are things that are proven. This is something that's going to be proven very soon. So this was 30 years ago. This was when I was your age. This is what was happening. Let me mention a couple of other things that were happening that you might not be quite so familiar with. These are also, I sort of enlarged the window a little bit because I wanted to make a particular point, but these are all basically 30 years ago. This is another famous paper of Shannon's, Communication Theory of Secrecy Systems, also published in Bell System Technical Journal. This is a very important paper today. Okay, there's a lot going on in this area today. This inspired a lot of today's research. I'll say a little bit more about it later. This is Nash's paper on Nash equilibria. Nash was a graduate student at Princeton. He got his PhD in 2 years, and this is the paper that describes his thesis. This is Proceedings of the National Academy of Sciences. And then this is a paper you may not be as familiar with unless you work in detection and estimation. This is the exposition of the theory of reproducing kernel Hilbert spaces. Okay? This was published in the Transactions of the American Math Society by Aronzian. Okay? So again, this is some more stuff that was happening back 60 years ago. What about 30 years ago? Some more stuff. Well, here's another important paper. This is Chizar and Kerner, Broadcast Channels with Confidential Messages. This is a follow-on to Aaron Weiner's celebrated paper on the wiretap channel. It's really the first paper to look at some of the ideas of theoretical secrecy or information theoretic security in one of our standard channels of information theory, broadcast channel. 1977, the year I got my PhD. This is another paper you may not be as familiar with. This is by Mike Persley, a former colleague of mine and Ken Jenkins in Urbana. We were there at this time. In fact, that's the year we went to Urbana. This is a paper on, this is when CDMA was people were first beginning to look at CDMA as a communications technique for multiple access. Mike liked to call it SSMA. He tried to change the tide, but Qualcomm pushed it back to CDMA. But this is a paper about how do you evaluate the performance of a CDMA system. Okay? And then this paper, I pushed a little forward because I wanted to get this paper, and this is Mike Tanner's paper on the use of bipartite graphs to describe error-correcting codes. Another paper that sat around for a long time and then came back with turbo codes and LDPC codes in particular, and has been very, very influential in the more recent past. So I pushed a little forward, not quite 30 years, but he was, I'm sure, thinking about this 30 years ago. So why do I put these particular papers up? Well, because in the second part of this talk, the one about wireless, the future, I'm going to talk about all of the ideas coming from all of these papers. Okay? So that's why I chose these ones in particular. And so lesson number 2 is the past isn't dead. It isn't even past. Okay, this is a quote from William Faulkner. But the basic idea is that a lot of things that happened a long, long time ago are still very, very important to what we're doing today. So that's sort of lesson number 2. Okay, then the third lesson is sort of more personal. Eileen had asked me to say something a little bit about my own sort of trajectory. So I have one slide on that, which is this one. And this is just, I look back, getting ready for this talk, I look back at my publication list to see, okay, where in the 30 years since my PhD, where have I published my papers, my work? And it breaks down basically like this. 20% of my published journal papers have been in the transactions on information theory. Okay, I wasn't surprised by that. 40% have been in various communications journals, TCOM, Transactions on Wireless, JSAC, and so forth. Another 20% have been in various signal processing journals, mainly Transactions on Signal Processing, but other journals as well, EuroSIP and so forth. And then another 20% in other fields, control, Transactions on Automatic Control, say, or SIAM, finance, math finance journals, and stochastic analysis more generally, annals of probability and so forth. So why did I put this up here? Well, again, the second part of this talk is going to draw on ideas from all of these areas, okay, not just information theory, not just things that were publishable or were published in the Transactions on Information Theory. So lesson number 3 is information theory is a broadly applicable discipline. It's not only about finding the capacity of channels, although of course it is also about that. It really covers many, many things, and it's applicable, it's very fundamental, can be applied in many places. So the lesson is be broad, okay? Don't narrow yourself too much, because there's a lot of interesting things out there in areas where you can make contributions. So let me just review the lessons. I'm being a good teacher now. I give the lessons. I'm going to review the lessons now. Lesson number 1, focus on the fundamentals. Lesson number 2, don't ignore the past. And lesson number 3, take advantage of the breadth of the field. That is, what you know now is very broadly applicable, and you should take advantage of that in your future career. And in fact, you know, we see from Toby Berger's work how broadly applicable it is. He's working on basically neuroscience now. And there are other examples where we have people working on, from information theory, working in many other fields. Tom Cover is famous for working on finance, for example. So be broad. Okay, that's the wisdom part of the talk, such as it's worth. And now I want to shift gears and talk about something that's a little more research-oriented, which is I'm going to talk about the future, and in particular what I see as sort of the future of wireless networks, more from a research perspective. And I'm going to talk about three perspectives. But let me first set the stage a little bit by saying a bit about where we are in wireless today. The past 25 years, which is most of my sort of professional career, has been a very active one in developing new techniques at the link level in wireless networks. Okay, that is, think about the things that have really influenced, like cellular communications or Wi-Fi or WiMAX or so forth. These are sort of the name. This is the alphabet soup that goes with that. CDMA, OFDM, you know, sort of the air interfaces. MIMO has been unbelievably important. Multi-user detection, turbo processing, not only for turbo codes, but for LDPC codes and other types of codes. So these are all sort of link level advances that have been major watersheds in wireless networking. So what about now? So today, I think we see a much more of a focus on interactions among nodes rather than multiple nodes, rather than just link node-to-node communication. We really look a lot more at what happens, how nodes behave as groups. And I'll just divide this into two different kinds of interactions, competitive interactions, and I'll give some examples which are very much in the news today, of our news anyway. Cognitive radio. This is a competitive type of node behavior where secondary users are competing to use the spectrum freed up by primary users. Security. I'm going to say a bit more about that later, but security is a competitive situation. You have two receivers out there, one that you want to receive a message and one that you don't want to receive a message. So the eavesdropper is competing with you to learn the message, and you're trying to keep them from knowing that message. And then what I'll call economics, that is viewing networks as economic systems, and I'll talk more about that in depth. And then the other mode is sort of collaboration, and we see that in all sorts of other things that come up a lot in research today. Network coding, that's a collaborative way of using multiple nodes getting together to do either error control or even security. Cooperative transmission and relaying, the name itself evokes collaborative behavior. Multi-hop transmission, that's collaborative behavior. You've got to work together to get messages across the network. And then collaborative applications. I'll talk a bit more about that in a minute, but that is having nodes that are working together on a particular application. So this is kind of what's in the air today is, looking at nodes more generally. So I'm going to talk very briefly about three perspectives that come from this. And they also sort of reflect these three main areas that I was talking about before: communication, signal processing, and information theory. So the first thing I'm going to talk about is what I call economorphic networking. This is not my word. This word is used already in the literature, but this really refers to the modeling of communication networks using economic ideas from economics. And I'll talk particularly about communication networks and competition, which is the main rule of the day in economics. Then I'll talk about what I call sociomorphic networking, which is more about collaboration, that is working together. And here I'll talk about sensor networks, so collaboration in sensor networks. And also to emphasize this idea about breadth, I'm going to here mainly talk about ideas from communications, here mainly ideas from signal processing. And then I'm going to talk at the end about secure networking. And here this is strictly information theoretic. And here this doesn't really fit into this more general sort of big word category. But it's sort of a new role for the physical layer. Or the question is this a new role for the physical layer? So let me just talk about these briefly in turn. And I'm not going to have time or whatever to get into much depth, but just to give you sort of an idea of what I'm talking about. So first of all, what about economorphic networking? What do we mean by that? Well, economorphic networking means that we think of nodes in this way. They can be viewed as economic agents, each seeking to maximize its own utility. So that's really the way economists talk, right? We're economic agents, and we are seeking to maximize our own utility. For network nodes, utility is not what our utility is, but it's energy efficiency or spectral efficiency or what have you. So some examples of sort of techniques that come from, that come from, oh, there's too many O's there, that come from economics, ideas that come from economics into networking from this view are non-cooperative games, that is, thinking of nodes competing with one another for network resources. Or auctioning, where nodes bid for network resources, for example. Or what are called coalition games, that is, games, repeated games where incentives are provided so that on successive playing of the game, nodes are incentivized to behave well, to do things like packet forwarding of other nodes' packets, for example. So what does this do for us in terms of, as engineers or as researchers? Well, it gives us new ways of understanding network behavior. It can give us some new design tools, and I'll talk about that in a second. And then it's also, but I'll just point out that it's based on the idea of a node as individual, that is, individualized node behavior. So a node is working in its own behalf, on its own behalf. That's the idea behind this, just like economic man, as the economists say. So here's an example, energy games. So here we have a communication network. These are terminals, and that's an access point. And this is the uplink. So this is an infrastructure network, a network with an access point. And the idea is that this is a multiple access channel. So terminals are transmitting up to the access point via a multiple access channel. The users are competing for resources because it's a multiple access channel. So whatever one terminal does affects all the others. So we can model this as a Nash game. So there's one of those papers I mentioned, where the terminals are economic agents competing for radio resources, and their utility, though, is measured in bits per joule, energy efficiency. So these are energy games. So we can look at Nash's idea of a Nash equilibrium from that 1950 paper, and that'll allow us to examine the fundamental trade-offs in network design as they affect energy efficiency in bits per joule. And a very nice formalism for this is due to what I call the WinLab school. There's some proponents of that here, which is this, looking at this particular formalism of the game. I listed a few names here, but many others have worked on this, maybe Eileen also, and Shenor, who's here somewhere. This is sort of, as I said, the WinLab school of network design, if you might say. But so we think of a game, G, where we have the players are the users or the terminals, so there are K of them. Each terminal has its own set of strategies and its own utility. And the utility is measured in throughput divided by transmit power. If this is bits per second, this is watts or joules per second. So this is bits per joule. So it's energy efficiency is the utility. And we can measure the throughput. So transmit power is pretty obvious, but throughput we can measure in this way. It's the transmission rate times the frame success rate. And the frame success rate we can write as a function of the received SINR, signal to interference plus noise ratio of user K. So after processing, but before detection. So the fact that we can write this in this way, by the way, sort of goes back to that paper by Mike Persley, because he was sort of one of the first people to look at the performance of CDMA systems, for example, using this kind of a model. So this brings that paper in too. So something from 60 years ago, Nash, and something from 30 years ago from Persley. So here's I'll just do a couple examples. This one is this looks at the Nash equilibrium of the game where we have, first of all, CDMA, random CDMA, K terminals and N, spreading gain N. Single input, multiple output, so multiple antennas on the access point. And we look at the asymptotic limit as K and N go to infinity, and well, the load is constant. So that just allows us to get rid of the random fluctuations associated with the spreading code. This is David Shea's idea. The terminals play the game by choosing their transmit power to maximize their own energy efficiency. So it turns out that this game does have a Nash equilibrium, and it involves balancing the SI and R at the base or at the access point. There's a lot of interesting stuff here, but more importantly, in the asymptotic limit, that is in the large system limit of random CDMA, we can write the Nash equilibrium energy efficiency in closed form. So we can use it to analyze various choices in the network design on energy efficiency. So here, this just looks at the choice of the receiver at the access point. And this looks at the match filter, the decorrelator or zero forcing multi-user detector, and the MMSE multi-user detector. And this shows average utility, which is energy efficiency in bits per joule, versus load. This load, which is a measure of spectral efficiency. And this is for the match filter in green, the decorrelator in blue, and the MMSE detector in red. And the two curves for each of these correspond to 1 and 2 receive antennas respectively. So you can see that when we look at things in this context, first of all, one thing we note immediately is that, as we would expect, energy efficiency and spectral efficiency are opposing goals. That is, as the spectral efficiency goes up, the energy efficiency goes down. This is known from information theory, right? Sergio Verdú looked at these wideband limits and the minimal EB over N0 that you can get, and you find it in the asymptote of infinite of zero spectral efficiency, basically. But it's the same shows up here in this Nash formalism as well. And you can see that the choice of receiver at the access point has a lot to do with the energy efficiency back at the terminals. Okay, so for example, the decorrelator in blue and the MMSE detector in red are quite different in this regard. In particular, if you look at the two antenna case, at 60% load, you see you get double the energy efficiency if you use the MMSE detector at the access point over what you get if you use the decorrelator. And of course, the match filter doesn't support that load at the Nash equilibrium. So it tells you a lot about, you can learn a lot about system design by looking at this economorphic way, looking at this in this economorphic way. Another example is we can look at the effects of quality of service constraints. This is the game that we play here. We now have a random CDMA again. Here we just look at the match filter. But we have constraints on the source rate and the delay of the traffic. Okay, so these are this is the QoS parameters, right? And the game the terminals play is they can choose their transmit power just as they could before, and bandwidth, transmit bandwidth. Okay, so it turns out that this game also has a Nash equilibrium, and we can write it in closed form. But it involves admission control because we can't. You can imagine that not every user with every possible QoS parameters could be admitted to the network forever, right? I mean, at some point the network just shuts down. So there's a notion of the size of a user. As long as the sums of the sizes are less than 1, you get a Nash equilibrium. So this just shows we can use that equilibrium to look at the effects of QoS constraints on energy efficiency. So this is an example. It shows energy efficiency versus delay. Everything is normalized here, so don't worry about the numbers. But you can see that this is delay. So as the delay, this is the delay, QoS delay requirement. So as the delay constraint becomes tighter, that is, as we move to the left down here, the energy efficiency plunges. This is an ARQ model. So that means that as we need a tighter delay constraint, we have to transmit with greater power to make that happen. And that shows up here. Also, we can look at the effect of source rate constraint on utility. This B is the total bandwidth. So if the source rate is 10% of the bandwidth, we get a significant loss in energy efficiency, about 20%, over the situation where the source rate only needs to occupy, the source is only rated, the rate of the source is only 100th of the bandwidth, for example, the channel bandwidth. So, you know, the point here is that we can analyze this very clearly, what these trade-offs are, using this economic view. There are a lot of other things we can look at here. We can look at other receiver choices, nonlinear multi-user detectors. But by the way, I just want to point out that both of those results that I showed you were published in the Transactions on Communications. Other papers also in this area, this is with Dongning Guo. We can look at nonlinear multi-user detectors as well, using the sort of asymptotic theory of random CDMA for nonlinear multi-user detectors developed by Dongning and Shlomo Shammai and Sergio Verdu. We can also look at the ultra-wideband, the choice of equalizer, which of course is a rich scatter environment. These are two papers that recently appeared. This is Giacomo Bacci and Marco Luisa at Pisa. We can also look at adaptive modulation. That is, the terminals can choose more than their rate and power. They could choose their carrier, for example, in multi-carrier CDMA, or the modulation index. That is, if you use QAM, how many points in the constellation should you choose? Or they can choose their spreading waveform. How do you spread to get maximal energy efficiency? We can also do other things besides Nash games. We can look at auctions. So we can think about using, suppose you have a relay and multiple transmitters that want to use that relay. Well, how do you decide how to make it happen? Well, one way to do it is to have an auction. Let the transmitters bid for the relay services. Okay? We can call these relay auctions, and this describes the behavior and also algorithms and protocols for assigning relays. In multi-hop, we can look at, again, repeated games. I mentioned this before, and provide incentives on multiple repeated plays of a game. So to provide incentive for nodes close to the destination to forward packets from nodes on the boundary. So there are a lot of things that we can do by using econometric or economorphic view of networking. So let me now talk a little bit about sociomorphic networking. So this is a sort of more collaborative idea, and I'm going to talk mainly about sensor networks here. So the idea here is that network nodes work together. So the idea in the economorphic view is that network nodes are individuals working for themselves. Here they work together, either collaborating, that is working together on a common goal, or cooperating, working together to help each other achieve their individual goals. Okay, so this is quite different behavior from the behavior I just described in the economorphic view. So what does this view do for us as researchers? Well, it provides new algorithms. We know this already about cooperation. New protocols, same thing. And it's based on a collective view of node behavior rather than an individualistic view of node behavior. So this is sort of the socialist side, and the other was the capitalist side. Okay. So let me give a couple of examples, and the examples will be in the context of sensor networks. So why sensor networks? Well, sensor networks, first of all, have a few salient features, wireless sensor networks. So first of all, they have a common application. The application is inference, that is detection and estimation, right? Also, sensor networks often have correlated information sources, that is, the sensors are measuring a physical phenomenon, and if their two sensors are close together, they're going to have similar measurements. Also, energy is severely limited in sensor networks. Obviously in communication networks, wireless networks, energy is limited. But in sensor networks, it's even more limited because typically you put sensors in places where people don't go, whereas your cell phone you keep with you all the time so you can recharge it at night. And again, the nodes typically have a common goal, and that is they want to detect something or estimate something or map something. So that's where we get this idea of collaboration. So in collaboration in particular, sensors work together to make inferences, transmit data, or what have you, And usually the overall constraint that they're working on is some kind of constraint on resources, so batteries and bandwidth. So again, I'll do two examples. These are both sort of, think about a situation where you can think about sensors that have been deployed at random in some physical area. The first one I'll mention is collaborative beamforming. So if we distribute sensors at random, they're going to naturally cluster together. Some of them will be close to one another. And sensors that are close to one another can communicate with low power because of the diffusion losses are low because they're close together, compared to their individual communications back to the access point or wherever they want to send their measurements for processing. So a natural thing for sensors to do in a cluster like this is to get together. And also another point is that if they're close together, they'll probably have redundant measurements or very highly correlated measurements. So a natural thing for sensors to do is to get together, decide on a common message together around here with low power transmission, and then get together and form a beam back on the access point, okay, by correct phasing of their antennas. So we could ask the question, what are the properties of a beam formed collaboratively in this way? And this question was answered. So this is distributed beamforming. There's been a lot of work on this area in recent times. The beam properties were studied in this paper with Hideki Ochai, Patrick Mitron, and Vahid Tarok, and now note that this is a signal processing paper. And it looks something like this. This is the average beam pattern. N is the number of nodes in the cluster, the number of sensors in the cluster. R is the radius of the cluster, and this is normalized to the wavelength of radiation. And you can see that we can form a very nice beam in this way. The side lobes are basically 1 over N, so that means that we're getting a gain of N out of this, energy gain of N pointing at the access point. And the other thing we can notice is that as the radius of the cluster gets larger, the main lobe narrows and the side lobes move closer to the origin or closer to the main lobe. So this is pointing at 0 degrees, this particular beam. Okay, so we can characterize this completely. We can say how high these are, where they are, and so forth. We can also, so this is a very nice beam we can form. We can also look at the effects of phase jitter on this beam and deviations from the average. This is the average, but what we're going to get is a realization. So we can also analyze that realization. And that's all done in this paper. Another collaborative, so that's collaborative beamforming. Another example is collaborative inference. So inference, again, is just detection and estimation. And that's the main application of sensor networks. That's what they're out there for. So there's a common application. Unlike a communication network where my goal is to get my packet across, in a sensor network, my goal is to be part of this network that's trying to do something, a particular application. Okay? So the thing that makes this an interesting problem, of course it's an interesting problem anyway, there's a lot of interesting inferential problems, but the thing that makes wireless sensor nets particularly interesting in this context of this application is that typically each sensor has only a subset of the total data, and because of the communication constraints, this data is distributed. So this is an inference problem with distributed data. Okay? And the division of this data sort of defines a topology. That is, these sensors are physically out there in some way, and they can talk to themselves locally, but they may not want to talk to some distant access point because they have to conserve power. So the topology of the network itself, the physical topology and the way the data is distributed in the network, shapes the nature of collaboration. And we can capture that by using sort of an idea from Tanner, 1981. That is, we can define a bipartite graph that describes the nature of collaboration here. That is, we can divide the vertices, we can put together a graph, divide the vertices into two parts. One part consists of the learning agents, which here are sensors. The other part consists of the data. Here, this slide I took from a talk on learning, so distributed learning. So this is a training database. The training data are somehow distributed out in the wireless network, and the sensors can access various data based on local topology. So in this graph, there's there are these vertices, and then they're connected by lines depending on the data that can be accessed. So learning agent 1 can access these three data points, and so forth. So this looks a little bit like a sparse bipartite graph that you'd see modeling an LDPC code. So for example, here's spatio-temporal field estimation. The data somehow has to do with the actual physical field, and the sensors can access those sensed measurements that are taken by sensors close to it. Okay, so that defines a topology. As I said earlier, we can map that into a bipartite graph. And in fact, just like in using the sort of Tanner graph idea to decode LDPC codes, we can also think about message passing algorithms as a way of doing inference in this environment. That is, once we have this bipartite graph, we can forget about where it came from, and we can start thinking about doing inference here. Okay? And in fact, there is a message passing algorithm. It's described in this paper in the Signal Processing magazine. This is Joel Pred, who's a former student of mine, and this is Sanj Kulkarni, my colleague. And in fact, this is where Aronzian's paper, I didn't put the formulas here, but what we're doing in this algorithm is we're doing RKHS, reproducing kernel Hilbert space curve fitting, and we're doing it iteratively using message passing. Okay? And it turns out that by doing this, you get coherent inferences of the underlying field with only local communication. Okay, so there ties in Aronzian and Tanner. Related issues, I'll just point to a few other papers here, a recent paper. Most of these haven't appeared yet, but there's a lot more that can be done in collaborative beamforming. That is, we can do what's called cooperative beamforming. There are message sharing protocols that we can do. We can look at power control. We can look at the issue of synchronization, and so forth. We can also look at opportunism. That is, if you're the access point, you could control which nodes transmit, and the nodes don't really have to know whether they're phased up or not. You could know that at the access point. So by using very limited feedback, you can actually do beamforming with the nodes sort of being dumb and not knowing their own phases, relative phases. There's a lot more also that's been done in collaborative inference, and here's some things. This is a paper that appeared in Information Theory a couple years ago on the issue of what you do when you have distributed inference and you have limited capacity links. Judgment aggregation is a problem that actually comes up in psychology. This is work done with Dan Osherson, who's a psychologist at Princeton. Has to do with how do you take disparate judgments of a panel and make them into one single coherent judgment. This comes up, of course, in sensor networks, too. That is, you've got all these sensors reporting in, and you want to put that together at the fusion center, and that's sort of the same problem. So this is an Informs journal, decision analysis, and so forth. I think I'll go ahead because I'm getting close to the end. So let me talk now about the last point I wanted to talk about, which is secure networking. And to set the stage for this, and I think maybe many of you already know about this kind of thing, but I just want to, for the rest of you, let me just set the stage. So now I want to look back at the physical layer again and talk a little bit more about, look at the context again of sort of how we use the physical layer. So, you know, in the beginning with wireless, the physical layer was considered to be an impairment. That is, it's a bad place. Okay? Much rather have an optical fiber. And maybe we would much rather have an optical fiber even today. But given that we have wireless, it used to be things like fading and so forth used to be looked at as impairments. Okay? But we know, because of the research of people who came before, that in fact we can use the physical layer properties to actually improve capacity and reliability. And sort of the poster child for this is MIMO. This is remarkable. This is before your time, but in the mid-90s when Foschini and others were working this problem, it was remarkable that you could get extra capacity out of fading. People just couldn't believe that at first. Now everybody believes that. Cooperation and relaying. These are ways of using the open nature of the wireless medium to improve capacity. Cognitive radio is a way of taking advantage of the openness of the medium to improve capacity. It'd be hard to do any of these things in a fiber or a cable. So that's capacity and reliability. What about security? Okay. Well, security has traditionally been a higher layer issue. That is, it's usually done by encryption. But encryption can be very complex and difficult if you have an ad hoc network or a mobile ad hoc network. How do you manage the keys for encryption, for example, in a MANA? And also, encryption is based on computational difficulty. It's not about fundamental impossibility. It's about, well, it's a really hard computational problem, so we're not so worried about whether it's secure or not, because we know nobody has a computer that good, okay? But information theory provides a way of looking at the fundamental ability of the physical layer to provide security. And this really goes back to Shannon's 1949 paper, okay, on the information theory of security systems, secrecy systems. You know, this is a very interesting area, and of course you've seen a lot of work in this area in just the last few years. But it's still theoretical. That is, we haven't really started building systems based on this idea. But you know, 15 years ago, this was theoretical too. Okay, so who knows, maybe this will result in something good. So just a very brief plausibility argument here. How can we use the physical layer to provide security in a wireless network? Well, a very simple way to look at this is to look at what's called the degraded case, where you have Alice and Bob. Alice wants to send a message to Bob. Eve, the eavesdropper, would like to hear that message, but Alice doesn't want Eve to hear the message. Okay, so you can, if Eve is has a stochastically degraded channel, meaning has a noisier, lower SNR than Bob from Alice, then Alice can take advantage of that by packing her constellation close enough together that Eve can't distinguish the constellation points, but Bob can. Okay? So it's a pretty simple thing. We believe, if you see this picture, you believe you can use the physical layer for security, right? Another way to look at this, too, is that the way that we design systems today is we use an implicit separation between encryption and channel coding, right? So encryption is coding for security, and channel coding is coding for reliability, right? So, you know, just like we do, there's this sort of separation of source and channel coding more generally in transmission, and we know that now that we shouldn't do that in many situations, finite block length or finite packet length and so forth, multimedia transmission. Maybe we shouldn't do that in secure coding either. So maybe we should get rid of the separation and put the security and encryption and the reliability encoding, that is the error control coding, together in one joint security and reliability code. So it makes sense both from sort of physical point of view, and it also makes sense from sort of what we know about information theory today that we maybe didn't know 60 years ago. So I'll just give an example, and then I'll wrap up quickly. I've got a few more minutes here. So this is an example. This is from a paper that just appeared this month. This is with Grace Liang and Shlomo Shammai. This is many of you know the information theory June issue is a special issue on information theoretic security. A number of people here have papers in that issue. And this is what's called the broadcast channel with confidential messages. And this is the channel that was proposed by Chizar and Kerner in that 1977 paper that I mentioned as one of the papers that I was going to draw on. Here we have two messages. This is a broadcast channel. Message 0 is a broadcast message for both receivers. And message 1 is a message only for receiver 1. It needs to be kept secret from receiver 2, which for that message is a wiretapper. Okay? And we measure the level of secrecy by the equivocation rate of message 1 at receiver 2. And this is a concept from Shannon, equivocation rate. This comes from that 1949 paper. It's also described in his earlier paper too, but it's used there to talk about security. So here we can characterize a secrecy capacity region where one dimension is the common rate, that is the rate of the broadcast message, and one rate is the secure rate, the rate of the secret message that we can transmit secretly to receiver 1 without receiver 2 hearing it. And the region is the area below the line shown here. This is an example. This paper covers more general cases. This is the Gaussian BCC with IID Rayleigh fading. The fading to receiver 1 has a unit parameter, and the fading to receiver 2 has parameter sigma 2. And of course, as sigma 2 decreases, this fading gets more severe. So what you can see is that as the fading on the receiver 2 gets worse, the common rate gets smaller and the secret rate goes up. Okay? But an interesting point here is that even if, so all of these cases that are shown here, except for the red one, receiver 2 is stochastically degraded relative to receiver 1. But for the red case, receiver 2 is not stochastically degraded. It's stochastically identical to receiver 1. So we can do secure communication even when the eavesdropper is not stochastically degraded because we can take advantage of the fading fluctuations. I don't have time to talk about this anymore, but it's a very interesting idea. There's been a lot of work in this area, and I'm just going to talk about some of the things I've been working on personally, but there's a lot of people working in this field. I don't want to give the impression that there aren't. But you can look, there are a lot of other interesting broadcast things, multicast, multiple antenna systems, scheduling, starting to add the higher layer in. The MAC channel also, there's been a lot of work. This is the multiple access channel with confidential messages. This is also with Grace, and it's in the March information theory transactions. Feedback has a role here. You know, in a lot of information theoretic problems, feedback doesn't really play much of a role. But in security, it has a major role, as does site information. And there's, for example, Denise is here. He's been working on secure source coding where site information plays a major role, and so forth. So I think because of time, I won't talk any more about that. So let me just summarize this part of the talk, and then I'll be done. First of all, what I talked about were three things here, three different views of networks, how we might look at them in the future. Economorphic, which is sort of a communications view. Sociomorphic, which is sort of a signal processing view. And then I talked about security, which is really an information theoretic view. Is this a new role for the physical layer? And we might ask the question, is the physical layer dead? When I was not too much older than you, in the early 80s, everybody was saying that information theory is dead. It's all been done. And that was just before wireless took off. And we've had a huge run of very, very important results in information theory. Well, is it dead now? Okay. Are we in the post-PHY or post-IT world? And the answer, of course, is no. It wasn't dead in 1980, and it's not dead today. In wireless in particular, the physical layer is always going to be here. But we are in a different world from where we were a few years ago. We're in sort of a PHY-MAC, PHY-NET, PHY-app world. That is, we're in a world where we have to worry about other things besides just the information theoretic issues. So, again, 3 lessons. You can't say you came to school and didn't learn anything, hopefully. Lesson 1, focus on the fundamentals. Lesson 2, don't ignore the past. And lesson 3, take advantage of the breadth of the field. And with that, I think I'll thank you.
Thank you, Liz, very much. Before we take the questions, we're going to delay the poster session for about 5 minutes. We'll take the questions, and now we'll take a group photo here and also outside. So with that, questions for Liz.
Ken.
Well, we hear a lot about optical communications. I know there's a lot of work right here in our department. And I wonder, what's your take on the future of optical wireless communication?
Well, I mean, a lot of the issues are similar. You know, I don't know if fading is such a big issue in optics. I really don't know much about the physical models. I mean, in radio, you know, fading is the number one thing. Fading and interference are the two things that really define the channel. And you know, optics, just interestingly, this physical layer security, which in wireless is kind of a recent thing, at least from the point of view of trying to do something practical. In optical systems and optical fiber systems, there already are physical layer security techniques. There are products that use the physical layer to achieve security in optical fiber. And that has to do with the fact that you can't really tap a fiber without it being detected. So, you know, in that respect, in some ways, optics is ahead of wireless. But I don't know much about free space. I don't know much about free space optics to really opine much. I mean, presumably a lot of the issues are the same, but I think because of the nature of optical transmission, you probably don't have quite the same issues with fading and so forth. There are probably other issues, scintillation and so forth. So, sorry. Mm-hmm.
Any other questions?
Yeah, there's one back there.
I have a question because I work on physical layer security, so I want to ask, would you say you are optimistic that physical layer security will one day be implemented in a real system? Because you just said it's still a theoretical issue at this point.
Yeah, I am optimistic, actually. I mean, I think there's some challenges, okay? But I think my guess is that with feedback, the practical systems will involve feedback, is my guess, of some sort, okay? The system I mentioned here, the broadcast channel with confidential messages, it's a channel where, it's a system where the eavesdropper is really a participant in the network. It's more like a situation where you have some messages you want to multicast and some messages you want to unicast, right? But the users are the same. It's not like a malevolent agent. It's more like, you know, somebody who hadn't paid for this service type thing. So in that kind of circumstance, all the terminals are participating in the network. You can expect to know something about the network. It's not like it's completely unknown. And then I think then you can take advantage of information theoretic security concepts to provide security. It's very difficult to think about something which is a worst case scenario. That is, an eavesdropper sneaks right up against you or has a huge powerful antenna. That's more difficult. But you know, there is a lot of work. I mean, for example, Greg Warnell has done a lot of work on looking at multiple antenna problems. And essentially, you have an arms race, just like you do in encryption. In encryption, you have an arms race between the complexity of the encryption device and the complexity of the cryptanalysis, right? If you have a big enough computer that you can factor the polynomials or factor the primes, then you can break the crypto system, right? So it's sort of an arms race. And in wireless, you have in information theoretic security, you have a similar arms race between, for example, the number of antennas at the source and at the intended destination, and the number of antennas that the eavesdropper is willing to deploy, for example. So you can think about the same kind of thing. You just have to make it expensive enough that your message isn't going to be worth deploying resources to intercept. So I think there are a number of issues here. There are issues with ordinary encryption too, which we're used to, right? But the issues here are just different. It takes a while to get used to them, think about what's the practical thing to do and so forth. But I do think that there will be things, particularly in like a MANET. How are you going to use, I mean, there are algorithms for key distribution and ad hoc networks, but they're very complicated. You have to distribute a lot of keys, right? And then you start moving around and you've got to worry about, are those keys even present in the other terminals nearby and so forth. So I think there are situations where encryption is just not going to work. And in those situations, the first line of defense is going to be physical layer. It's a good question. Okay, maybe given the time, we should.
And shameless plug, we do have physical layer security in IT MANET.
Yes. Yes. Not so shameless.
Well,
yeah, okay. Thank you again. Thank you very much.